So in this video, I'm going to cover how to do mediation analyses with a focus on the traditional steps listed by Barron and Kinney and their sort of seminal paper on mediation. It also includes a lot of Hayes work with process and that plugin for SPSS. I will warn you that there are lots of different alterations to this type of design. Dave Kinney has a bunch on his website, and Chris Preacher on his site talking about simple slopes. Sorry, not simple slopes. The SubL Test, and then I would just warn you that there are lots of different ways to do this, but this is the very traditional way. Okay, so what we're going to do is look at dataset 6 on Blackboard and work through a mediation design where we think that the treatment condition they're in, this first column, treatment condition affects their number of days that they're housed. So what's going on in this study is we have like temporary housing, and we're looking at how many days that they're housed. And so we have two different groups, a control group and a treatment group. But we think that the number of housing contacts they have mediates the relationship between condition and days housed, so that there is a change in the relationship between conditions and housing because of the contacts. Okay, so this isn't that at each level of contacts we get a different relationship. It's that the relationship between housing and contacts essentially goes away when we add that third person in. So the way to think about mediation is that it's sort of the third variable issue. And so I always think about it as, like, in the lawyer sense, there's a mediator, someone who changes the relationship between two things that can't get along, essentially. But also you can think about it like your friends. So you and your friend are in the room, you're chit-chatting, blah, blah, blah. When that third person comes in, it does change the dynamics of you and the first person talking. Okay? So that's the basic idea behind mediation. All right, so for power, what I'm going to do is use G-power here. And it's the same power we've been talking about for regression designs. So test family is F, right? Statistical test is going to be multiple regression, fixed model, deviation from zero. And then we would just enter what's our R squared, what's our alpha, here's beta, power, which is 0.8. And the number of predictors in this simple kind of mediation is going to be 2. At some points it's 1, but generally it's 2, the important part, and we can calculate. Okay. That's a really simplistic way to calculate power for mediation. Like I said, between Kinney and Preacher, you can probably come up with 10 different ways, but I think that's probably the easiest one to do, is sort of a quick estimate, but I would recommend you read some of their work if you really wanted to know like the best way to estimate power for mediation. So it says we need 68 people, and then we've got about 100, I think, 100 and something, so we should be good. All right, let's talk about data screening. Now, remember that the process plugin is run in a separate way. So normally when you screen for regression, you can do the actual regression and screen at the same time, but in this particular case, we're not going to be able to do that because we're going to run the mediation in a separate window. So what we're going to want to do is data screen and then run. Okay, so let's check for missing data and accuracy. So analyze, descriptives, frequencies. We'll move over all three variables. And then under statistics, at least min and max, but I also usually recommend the standard deviation and mean. Okay, continue, and okay. So I don't have any missing data, which is good. I don't have to estimate anybody. It looks to me like my treatment groups don't have any weird codings going on. And then I would have to know the upper and lower limits, but clearly I can't be housed negative days, and so there are no negative numbers, which is pretty good for us too. So this is where I would check for like typos and any missing data. All right, so let's run an outlier analysis, and there's going to be 3 parts to this. So we don't need to do a fake regression because this is real regression. So we're going to do analyze, regression, and then linear. We're going to put our DV in dependent, which are this example is days housed here. And then both our IV and our mediator in independent, because we're sort of just trying to screen things right now. Now, treatment is a categorical variable. It is one or the other. So if your output, when you screen with categorical variables, looks totally crazy, try taking it out and screening it again and seeing if that's what's causing the issue. Because sometimes you'll get like these flat lines where it's clearly just separating them by group. Another thing you could do is split your file on the categorical variable and screen each piece separately, essentially. That's also an option people like to use. I always just try it with the categorical variable because I am going to use it as a predictor and see what happens first. Okay, so let's see. We want to get just the stuff for screening since this isn't the actual mediation test. So plots, z-pred and y, z-residual and x, histogram and normal probability. Continue. And then save, and all three of the distances, Mahalanobis, Cook's, and leverage, remembering that there are a bunch of different outlier statistics. It's just these three are the ones we've been learning, and they're sort of the best bang for your buck. So hit continue, and okay. All right, I'm going to hit the star button to go back to the data, and we're going to do, since now I have a lot more people than the other examples on my channel here, I'm going to do a transform, recode into different variables to kind of check for all the outliers. And this is what I've been saying where, you know, when you have 10 or 20 people, it's easy to just kind of look at the data, but when you get hundreds of people, this will make it much easier on you. So we're going to use the transform window and recode into different variables. So first thing I'm going to move over is Mahalanobis. And you have to give it a name before you can do anything. So I'm going to call it all out for outliers, for Mahalanobis, and hit change. Click old and new values. And this is where we're going to code everybody who's an outlier as 1 and everybody who's not an outlier as 0. So the first thing I have to figure out is what is my cutoff score. Well, that's what my chi-square table's for. So I have two predictors. K is 2. It's both the IV and the mediator. And then I'm going to use 0.001 because I want it to be really different before I cut anybody out. And so I'm going to do 1382. Okay. So 1382 is going to be my cutoff score for Mahalanobis only. So we're going to use this range value through highest. Okay. And what that's going to do is it's going to take everybody who has a 1382 and up and code them as a 1. Everybody else is going to be coded as a 0. So range value through highest means this score and up is going to be 1. Click add. And then all other values, everybody else is going to be, a 0. And then add. And that codes everybody as 0 is not outlier, 1 is outlier. Continue, and okay. So what that did is it put that one outlier there at the top. Okay, so they're the only person whose score is above my cutoff. Now let's do Cook's. So transform, recode in different variables. I'm going to hit reset. They have very different cutoff scores, so you can't do all of them at once. Let's go Cook's here, which I'm going to rename as outcook. Change. Click old and new values. And we're going to use that same principle, value through highest, but with Cook's cutoff. Okay, so the formula for Cook's is 4 divided by n minus k minus 1. Remembering that n is the number of participants, k is the number of predictors. So we're going to have 4 divided by, I have 109 people, minus k, which is 2, minus 1. Okay, so that's 4 over 106, which is 0.038. I'm going to make everybody at that score and higher a 1, hit add, and then everybody else, so all other values, a 0, and hit add. And then hit continue. Okay, it's going to make us one more column. So I have, let's see, descending here, 2 Cook's outliers. Okay, so I have 2 people over that cutoff score. You'll see there's a big break here. So if I sorted Cook's descending, you'll see that there's a big jump between most of the participants and then these top 2. One more time for leverage. So transform, recode into different variables, reset. Centered leverage, let's call it out. lev, change, old and new values. So what's the formula for leverage? Well, it's 2 times k plus 2 divided by n. So that's 2 times 2, because k is 2, plus 2. So that's 6 on the top divided by 109 is 0.055. Oops, too many zeros. Goodness. Bye-bye. There we go. So 0.055. I'm going to make them ones. Hit add. Everybody else can be 0. Hit add. Continue. Okay. And that means we have, let's see here, descending, 4 leverage outliers. So there are 4 people who are over the cutoff for leverage. All right, now what do I do with all that information? Excuse me. Well, what I'm going to try and do is come up with the people who have the best, who have 2 out of 3, not the best, who are have 2 out of 3 outlier scores, because that's usually good criteria to say, okay, I should eliminate them. You know, we've been talking all year about Multicollinearity and how it's used all by itself, but when you're talking about regression, you can have people who are far away from the rest of the points, and those tend to be called discrepant. Their scores are not close to the rest of the data, but they might be perfectly in line with the regression equation. Okay, and that would be leverage. So leverage is how much they're changing the slope. Discrepancy is how far away they are. Well, somebody who's, you know, whose data is not really that close to the rest of the data, but is within the equation that I'm expecting, it's not really an outlier. They're just, I mean, they are, but they're not like that big of a deal, really, because they're still within what I would have, a range of data I would be expecting. But people who have a high leverage of the slope, like their scores changing the slope a lot, that really draws into, okay, so why are they changing the slope a lot? So as always with outliers, kind of look at like, why are they outliers? Okay, and a lot of times it's because they're at the top or the bottom of the distribution, which isn't too surprising, but like, why are their scores what they are? Okay. All right, so how do I determine who has 2 out of 3, other than I can visually kind of see it right now because of the way I have it sorted. But if you have lots of data, this may be confusing. So the easiest thing to do is create one more column, so transform, and then compute variable this time. We're going to call it Outliers Total. Now you're just going to add all 3 of them together in the numeric expression window. So out for Multicollinearity plus out for Cooks plus out for Lev. So just add them all up. Don't add the original columns together because that score won't make any sense. So you're adding the 3 new columns we created that are 0s and 1s. Then hit OK. And now I can tell how many of them have 2 or more as their outlier scores. So these 2 participants here are outliers because they have at least 2 markers for them. And so what is it about those 2 participants? Well, they're different treatment groups, so that's not it. They're not at the top of the housing one, right? And they're not descending here. Well, one of them is at the top of the contacts one, so it's not clear that it's like, oh, okay, well, their scores are really high on either condition or either variable. So you'll want to sit down and think about, like, why are they outliers? And so that will make sure that you can explain why you eliminated them. So for what I'm going to do, I'm going to delete these 2 because they have 2 out of the 3, so that output that you are looking at in the notes matches what I'm doing on the screen. So that's outliers. Now let's look at multicollinearity. Well, the only 2 variables we have are going to be treatment and housing contacts. So we're going to check X and M and make sure they're not too multicollinear because they do get used together in the same regression equation as part of the steps. Right, so analyze, correlate, bivariate. So treatment and dazed houses are DV, sorry, treatment and contacts. Oops. And then hit OK. So this is technically a point by serial correlation because treatment condition is dichotomous. And yes, they're correlated, which is good for us. We do want them to be correlated. If they're uncorrelated, mediation's not going to work, but they're not too correlated, so that's good. All right, so I can't look at all this data because I deleted people, so I'm going to rerun my regressions. Analyze, regression, linear. It's still all set up. Hit OK. But one thing you will notice when you rerun it, you get more outlier statistics because you just reran it. Don't double delete people. Okay, these were not outliers the first time, so don't delete them the second time. So I'm just going to ignore those columns. You can delete them if you want. So let's go back to the output and look at normality. And here's why I said sometimes it'll look funny. So this is the normal curve for days housed given these other two variables, but one of them is categorical. So I think that's probably why you're seeing this hump in the data, this double hump, because there's two separate groups, and maybe this is group 1 and this is group 2. So you may consider taking out that categorical variable to be able to screen the data for just the continuous conditions, because you can't really change the category variable, right? So if you see this sort of thing, that might be a time to take the variable out and try it again. But in general, most of the data is pretty normal. It is from 2 to 2, and then with the caveat that this bimodal hump thing is probably due to the fact that there's a categorical variable in the mix. Let's go down to linear. And yeah, that's messy right there. So that's not good for you. So this would be another good clue that maybe something about the conditions is different, which is the point. So I might run it without. And then this thing for sure with homogeneity and homoscedasticity, the reason that you get this is because it is a limited data, right? So it can be 1 or 2, and so that's sort of why you're seeing it look like a triangle. But for and then generally, it actually does not really meet the assumptions. Homogeneity, it does this way, but not this way. Homoscedasticity, that is like a flying car, so not so good. So what I tell you to do in that situation is try that regression one more time without the treatment variable. Let's see what the continuous variable looks like. Well, it was sort of right. So something's going on here where we do have a strange distribution. So I don't know that this is really very normal because the peak should be over 0. So that's kind of problematic. And it might just be the way that data set is. We have at least 30 people, so we can kind of get away with normality. This is also bad. Okay, and then the data changed a little bit, but you still have this restriction of range, it looks like. So essentially, these assumptions are crap. But it's just an example, and I tell you to kind of dig into why your assumptions are not being met. So maybe it should be an x cubed function, because this is starting to be an S curve. And maybe we shouldn't assume normality here. So different things to check when you're using categorical variables. All right, but the point is to show you how mediation works. So what I'm going to do is run a mediation analysis. So analyze, regression. We're going to use the process plugin because it's fantastic. All right, so how does all this work? Well, this is going to be model 4. Remember, model 1 is basic moderation. Model 4 is basic mediation. So we're going to stick our y variable, or dv, into y. So that's days to house. So we want to know how many days we're going to have to house them. Our treatment condition is x. And our housing contacts is m. Now, in moderation, it does not matter if you switch x and m because it's an interaction, so it just depends on which way you want to look at the simple slopes. For mediation, it really does matter. So make sure you understand the conceptual picture that you're trying to make. And the cool thing is there's a templates file. It'll find it. Is it going to open? Lies. There it goes. As part of the package you get when you download processes, you get this templates file. So it shows you the pictures of all of the different designs that have been programmed in. So let's scroll down to 4. Here's 4. And you really cannot switch x and m. So this is more of a theoretical order that x leads to y, and then x leads to m. But if you put m in the equation, x to y is changing. So make sure you have which one's which here. Okay. All right, so we're going to leave the model number here as 4. Leave all this stuff alone. under options, what you want to do is pick the first four. I'm sorry, that's moderation. So if you pick effect size here, because we want to get kappa squared, the SubL test to test if mediation happened, and then the total effect model and compare the two models. Okay, so the bottom four, essentially all of them, that's a 4. Continue, and then go. All right, so let's talk about the steps to mediation. Oh, goodness, I have no idea what the heck word. There we go. I'm in a blank document here. So the way that Baron and Kitty have described mediation is that first you have to have that your x variable predicts y. Because you're saying that x changes with m in the equation, so if x doesn't predict y, then you kind of miss the point. This is considered path C. The second thing that has to happen is that x variable predicts m. Okay, that's path A. So I'm saying that x predicts y. So I have to establish that there's a relationship there first. And then I'm saying x has to predict m because I'm saying the path is going to be diverted through m. So this is like to a diverging roadway. And then the next piece is two things together. So we're going to put x and m together predicting y. But specifically, we want to know that m variable predicts y. And that implies that the diverging path continues past m. It doesn't just stop. Because then you just have x predicting m and x predicting y. And you're saying with mediation that instead of going x to y, it actually should go x to m to y. So you're predicting a separate pathway with a third variable involved. So if m doesn't predict y, you're kind of don't have mediation. So that is path B, traditionally. And then x still predicts, or x variable no longer predicts y. Or is lessened, predicting y. With m in the equation. And that's path C prime. And the whole point of mediation is that C and C prime are different. And usually that C is greater than C prime. You want it to go down. So you want to get closer to 0. And now it would be interesting if they flipped signs, but that might be a better indication of moderation, that there's actually an interaction going on. And so the argument here is that I have x to y as my one path. So I can take this highway from city 1 to city 2. Or I can have x to m to y as my second path. Well, I can take the loop around the city to get there faster. And when you add that loop, less people are taking the other highway. So it's like you're diverting the relationships. Now, that is the order that they have proposed that you go in, because if step 1 does not happen, it doesn't matter for the rest. And then if x doesn't predict m, the rest doesn't matter. And if m doesn't predict y, the rest doesn't matter. So they're in order for a reason. But sort of cleverly, the output that you're going to get is in alphabetical order. So we kind of have to match this to the to the output that we're looking at. So I'm going to do this kind of one piece at a time here. I'm going to highlight the whole thing, but we'll go through it one part at a time. So, you get all this crazy output. What next? Let's see where I'm at here. So the first thing it tells me is what I did in my analysis, which is nice because it reminds you what you picked as x, m, and y. And then the next thing you get here is this outcome is housing contacts. So housing contacts is actually m, and then the one variable down here where it says treatment is x. So this is x predicting m. And so that is actually number 2 here, x predicting m. So if you can't figure out what pathway you're trying to talk about, go in and label them as x, m, and y, and then match it to the step. So that overall model is significant. What you'll see sometimes is people put in all of the F statistics in like a table, and sometimes people ignore it and then just talk about the the coefficients. You could do both. I'll kind of talk about both here, but let's get rid of this so we can pull it up one piece at a time here. So the first thing I'm saying is that path A is significant. Okay, so I could do 1 and 1 of 5 is 8.87. Okay, so I'm going to use these numbers here to talk about degrees of freedom 1, 2, and then here's F. So P is it's less than 0.1, and then R squared, right, is equal to 8%, basically. Okay, so that overall model is significant. And then the predictor, which is probably the more important part, so let's go, it's B, lowercase b, for the coefficient. So how do I know, lowercase, thank you, word. So B here is listed under coef, so it's this number, 1.88. My T statistic, remember the degrees of freedom is the second one of the F statistics, so it's 105 here, is here under T, so it's coefficient standard error T, so 2.98. And P value is going to be the same P as before, because there was only one variable, so it's 0.01. Okay, so here's P here. So what am I saying? Well, I'm saying X predicts M. So treatment condition predicts the number of housing contacts they have. This is coded where let's check. I'm not sure, actually. This is coded where 0 is control and treatment is 1. And so if you're looking at dummy coded variables, that means B is the difference between the two. So treatment condition has 2 more housing contacts than the control condition if I round up. Okay, so there's more housing contacts in the treatment condition, which is good. That's what we wanted. It needs to be a predictor. Okay, so that's the first one is A. So let's look at the second one here. The next thing we're going to get is B and C prime. Like I said, alphabetical order. So this is going to be Y. And then we've got M and X together, which makes it this part here. And then the first one that comes up is M predicting Y, so that's path B, so that's here. And the overall model for this piece is significant. So both of them together is a significant predictor of days housed. So it's 2 and 1 of 4 is 1682. P is less than 0.01, and then our R squared, cheat here and copy, is 24%. So a big effect size. Now what about M by itself? Does it predict Y? That's an important part. And it does. So lowercase b is 1.73 here, so this is B. So for every 1 housing contact, we're getting 1.73 days housed. T is going to be 104, because remember it's the second degree of freedom here, is 4.96, so here, and it is significant, which is good, because it has to be, so less than 0.01. All right, now what about C prime? Okay, so it is X predicting Y, and so that's X predicting Y, but it's going to be C prime because we've got M in there. So M is tossed in, so be sure you're doing this one as C prime. And so let's see here. We want this to be non-significant in the perfect world, but we're also going to use the SubL test. So 3.455. The T value here is 104, right? Still, it's 2.36. No, I'm sorry, that's standard error. Got a line off. Oops. So B standard error here, it's 1.50. And then P is equal to 0.14. So it's actually non-significant. Well, that's good for us. That actually follows the path that we would expect. Okay. Now that doesn't always happen. Sometimes it's still significant at this step, so that's partial mediation. But what we're going to do is use the SubL test to sort of show that it's significant, that C and C prime are different when using M. And so if this step is significant, don't freak out. The very last thing you get is labeled nicely total effect model, and that's the first picture. So like I said, they're in alphabetical order. You get A, B, C prime, and then C. So the overall model is significant. So 1 and 105 is 7.38. P is less than 0.01 or equal to 0.01 if you want to round up. So I use these numbers here. And then R squared is 7%. Okay. So overall it is significant. Cool. The next thing we want to do is talk about what's the path, right? So that's here. So we got X predicting Y. And so it's 6.82. Our t-value with degrees of freedom 105 is 2.72. P is the same thing, 0.01. So the most important step, where X predicts Y, actually comes last in the output, but that's okay. I filled in all of them. Do I meet the criteria? Yes, X predicts Y. Yes, X predicts M. Yes, M predicts Y, controlling for X. And then X appears to go, or the path C, where X predicts Y, controlling for M, appears to be lower. Because look at the comparison. I've got 6.82 versus 3.55. Okay, so as the treatment condition is 7 days different, control versus treatment, with no mediator present, and it's only 5 days different with the mediator present. So you're seeing a lessening in the number of days we're having to house people when you control for contacts, essentially. So contacts changes the relationship between the treatment condition and the number of days housed. All right. What happens here is that you get everything again, essentially. So this is actually C. So the total effect of X on Y is C. The direct effect of X on Y is C prime. So it gives you C and then C prime. And then this indirect effect is C, oops, sorry, I shouldn't have deleted that yet. This piece here is C minus C prime. So 6.82 minus 3.55. That's where this effect number is coming from. Okay. And you notice there's no statistical test out here because it's down at the bottom. But it does give you the bootstrapped confidence interval. So the bootstrapped confidence interval tells you if the effect, the difference between the two, crosses 0. So if C minus C prime includes a 0 in its confidence interval, that means there's no difference between the two. So you want to see that this confidence interval does not cross 0, because that implies that there is a difference between the two. Okay? All right. The next couple of things we're going to get is a bunch of different types of effect sizes. If you're interested in this, I really recommend Andy Field's book with the SPSS version, talking about what all these things are and how they're calculated. It's also in Hayes' process book. And there's just lots of different things going on here, but I'm going to suggest using the last one, which is Preacher and Kelly's kappa squared. Okay. So Preacher and Kelly's kappa squared, I think is probably the best supported, is like the one that makes most sense to me without getting too much into the math. And so the effect here is kappa squared, and you don't want that to cross 0 either. But if one crosses 0, usually the other one does too. I'm going to use that when I talk about this last piece. So this is a bunch of stuff at the bottom. So after all of these steps are supported, most people do the SubL, what's called the SubL test. Okay. And that's the normal theory test, as it's listed here in the output. It is a z-score test if the indirect effect, or C minus C prime, is different from 0. So if it's basically saying, is it greater or less than 0, or like it is not 0 in some form, because it might be negative. The order of the difference might have changed between them. And so it's testing this 3.26. Okay, remember that's C minus C prime, and here's the z-score for it. So the way you write up the SubL test is you say z equals, and you write in z, 2.52. you list P, and you do want this to be significant, saying that there is a significant difference between the two paths. And then I tend to list kappa squared here to show people how big that difference is. So remember, effect sizes are important. How different are they? So let's find kappa here. It's a little k. It's a cute little k. Here it is. So we're going to kappa squared. We're going to put it in a font that we like. There we go. So the squared equals 0.13. You can interpret this the same way we interpret r squared, and that's about a medium effect size. Okay, if you go with 0.01, 0.09, 0.25. And so that's basically saying that the mediation did happen. Having this full picture of all three variables at once is important. So it's important to understand that x and y are related, but x to m to y are also related. So I got to remember that that third variable is useful and interesting and is part of the equation. Okay, so this is one good way to test for the third variable problem. Okay, so all that being said, that's going to be slightly different than the notes, it looks like, because I didn't delete people when I ran it that way. What do I want to report in my outputs? Well, generally, if you want to report the F statistics, they can go in a table. Most people list the T values that I've included to show which ones are significant, which ones are not, for sure. And then a little chart of that relationship. So making that triangle picture of X, M, and Y, and including those B paths on there is a great picture for this. So there's no like graph of this sort of analysis. It's more tends to be a depiction of the mediation relationship with those path coefficients, so the B values on the picture. But you'll want to label them as path A, B, C, and C prime, because that's the traditional nomenclature in this type of analysis. So that concludes mediation analyses using process and SPSS.